So a lot is being written and said about deep learning and the new AI wave. And not everything is true. So here's one of the things that's not true. So the idea that machines program themselves these days, and all we have to do is put mediocre data in, turn the crank, and out come excellent results. But there is what I think of true magic in this deep learning. And here's what really fascinates me the most about this field is deep learning lets us solve problems we don't know how to program. So we can solve problems we actually don't understand in detail, in sufficient detail that we can program a solution. The first time I witnessed this is quite a while ago. It was around 1992. I was at ETH in Switzerland working on a reading machine for the blind. And we made good progress on printed text, but we got nowhere for handwritten text. And so I was reading through paper after paper with promising titles and just to be disappointed time and again. So most people back then, they worked on capital letters from A to F, for example, did tiny variations to the bitmap and then called it font invariant. And then somebody pointed me to the work of Jan LeCun, and I looked into that and was very fascinated because he was working with actual data from the US Postal Service, no cheating possible. And he claimed to have excellent results, and his methods were comparatively simple. So we rushed to re-implement this, and well, first we had to rush to actually collect data and then train the network, and it felt like magic. It would actually read and do this seemingly impossible task. So a year later, I was fortunate to join that very team at Bell Labs. So I divided my presentation into two parts. The first part I will talk about the early deep learning work at Bell Labs, and then the second part I will talk about our current work at NVIDIA on self-driving cars. So from 1985 to 1995 was a 10-year period that was incredibly productive. So in that team not only created convolutional networks, it also created support vector machines, SVMs, and laid the foundation of important machine learning theory, and also created several generations of neural network chips. This is the building in Holmdel, New Jersey. So gigantic building, actually. It housed about 6,000 employees. 300 of those were in research, and 30 of those were in machine learning. So you probably recognize several of the names. And since, as researchers, we tended to show up late in the day, we always had to park way out here, which added about 10 more minutes to your commute just to walk into the building and into your office. There's these two ponds here. Could you imagine what they are for? They're not just landscaping. Yeah. Yeah, these are the heat exchangers for the air conditioning of the building, or used to be. Later they replaced them with cooling towers. This is the very first data set that they worked with, collected among the researchers themselves. Later they got data from the US Postal Service, and then that grew into NIST and MNIST, which is still very widely used today. So a lot of the work was about what structure do we put into the learning machines, what prior knowledge do we equip them with to perform the task well. If you look at this example here, and you needed to build a classifier that can distinguish between the red and the green classes, and you wonder what class does this X belong to. So if you take location, east, west, north, south as your criteria to classify, then you would probably say the X belongs to green. But if you understand that these points are actually real points on the surface of the Earth, and it happens that the green ones are on water and the red ones are on land, then you could change your criteria and say, we take the level above, the height above sea level as the criterion, in which case the problem becomes trivial. So this point is actually on land, so it belongs to the red class. Anybody see where this is? This is Manhattan, New York. So this is an example how programming or using prior knowledge actually helps the classification task enormously. Of course, that led to the creation of convolutional networks. This is an old slide that we use to explain how they work. Naturally, you have these convolutions that can learn to do detect lines, vertical, horizontal, and then next layer can detect edges and so on. And of course, the leap of faith was that we don't hand design these features, but actually let a numerical optimization algorithm find optimal solutions. Here's an old video from Jan LeCun showing LeNet. This was on an old AT&T PC, I believe, with a DSP accelerator in it. So you may have seen the video. It's on YouTube. And at that time, many, many, many brilliant minds tried so hard for years to solve the problem. And here comes this network and just does it with, almost looks with ease. And then Jan gets creative. I'm quite sure that this type of characters were not in the training set. Some other people from the lab. This is Tony Henderson and Rich Howard, who was the lab director at the time. So as we became to look at learning is essentially two main things. One is to build prior knowledge into the architecture, or what Vladimir Vapnik calls structural risk minimization. And the other one is capacity control. So you need to match the size of your network to the amount and the diversity of the data that you have. And one really good tool to do that, or to analyze that, is learning curves. So this is not the number of epochs here. This actually, each point on this chart is a fully trained network. So what you do is you measure the performance of your network on the training set and on the test set, while you're growing the amount of data that you're training the network with. So this is the number of examples that you use for training. So if you have very, very few examples, then the network can essentially memorize the training set, and the error on the training set is 0, while the error on the test set is very big. And then as you grow the data set, the error on the test set comes down, and at some point the network can no longer memorize, and the entire data set and the training set error starts to grow. And empirically, it's been shown that these curves, eventually they meet, and you don't need to plot the entire curve. It's usually in the middle between the two curves, so you can have a good idea what to expect. So if you hit this point here, then it becomes clear that it doesn't help you to add more data. You have to increase the capacity of your network. Here's a learning curve from real life that we did last week. So this is here predicting the steering angle of a human. So how close does the network steer like a human? And you see that around here we reached a point where adding new data wouldn't help us. Then in the 90s, there was sometimes heated debate about what is the best algorithm for classifying characters. And the manager of the group at the time was Larry Jackal, and he said, well, let's just find out and compare all of those. So this was one of these ideal situations where you had several people competing with ideas, and everybody was convinced my idea is the best. So we compare them all. And if I remember correctly, that's the reason where they created the MNIST database for. So M stands for modified. The result is somewhat interesting. So K nearest neighbor, that nobody believed that would be the winner. That was just there for reference. Also, fully connected network were just there for reference. Then this is LeNet 1. This was optimized for a much smaller data set from the United States Postal Service, so that didn't do very well on this either. In fact, it was even slightly worse than fully connected. And then these were the actual competitors. So this is a convolutional network, but this time optimized for the larger MNIST data set. I'll get back to boosting in a minute. Then different variations. So here, for example, K nearest neighbor, of course, has one big flaw. So if you just take the Euclidean distance as your metric, as we did here, then if you shift two characters, which are actually the same by a few pixels, then the Euclidean distance starts to become enormous. So it doesn't really measure how close to or how similar two characters are very well. So here the idea was that instead of using the Euclidean distance, let's do the same thing. I mean, use the Euclidean distance, but not in the pixel space, but in the uppermost feature map. And that boosted the performance quite a bit. Tangent distance was another one of the ideas we talked a lot at the time. Another clever trick to increase the performance of K nearest neighbor. So if you picture each character to be a point in a very high-dimensional pixel space, and you start doing some perturbations to it without changing the actual character, so you rotate it a little bit, you shift it, you grow the stroke a bit, then that forms a surface around that point. And if you don't deviate too much from the original point, then you can model that as a plane. And the tangent distance is simply the Euclidean distance between two such planes. So clever idea with a lot of prior knowledge of the problem built into, and that also gets very good performance. And optimal margin, that's essentially an SVM. And so what's interesting is that they all have the exact same performance. The only one that actually improved the performance was boosting, which is kind of a different type of approach. So here, you train multiple networks. You train the second network on the mistakes of the first one, and you train a third one on where the first two disagree. So you get multiple experts that specialize on different parts of the training set. And so it's not too surprising that actually would increase the performance. So what Larry said in hindsight is that, well, it's not too surprising that they would all perform the same because everybody was doing the same type of approach in exploring the best capacity of their learning system by doing the learning curves. The one thing that stands out in my mind is the SVM, because that has no prior built-in knowledge about the task at all, where all of the others do. Classification rate is not the only thing that you should actually focus on, of course. It's also memory consumption, which is not on this chart, training time and inference time. So all of the memory-based K nearest neighbor types, they use very little training time, but then they use a lot of memory. So the lessons, some of the lessons that I took from that time is, one is still very relevant, is look at the data. I've seen so many people miss important cues, confuse YUV with RGB, for example. That doesn't make your system fail completely, it just doesn't perform as well as it could. Solid debugging tools are critical. These neural networks have a nasty habit of masking bugs. They learn, they adapt, they try their best to work around bugs. Validated training data, again, that's related to look at the data. So many data sets I've seen actually have grave labeling mistakes. And the work is experimental in nature, at least. That's what it is, the state of today. So in most cases, you can't just copy-paste a recipe from somebody else. That will not give you the optimal results. And the last one is work with real data. Synthetic data is great for debugging, and you can certainly explore certain trends, but to get a sense of where you really are, you have to work with real data. So what happened after 95? Actually, right around in 95, the AT&T released first production version of convolutional networks for commercial check reading. And eventually, 20% of all the checks written in the US were processed by that system or read by that system. To me, that was the real sign of success if technology is commercially viable. In the same year, actually, we were in the morning sitting together discussing how we should celebrate this fact, this success with the commercial check reading, when the message came in that AT&T, the announcement came in that AT&T would break up into 3 parts. So that was quite a shock. And then in 2002, there were mass layoffs and most people left. And some of the important folks from machine learning, they found themselves working together again, either at DARPA or for DARPA, and created several programs such as Lager, learning applied to ground robots, learning locomotion. One was even called deep learning, and also were helping to get the various different DARPA challenges launched. And then in 2002, deep learning becomes really popular, and I guess it's triggered by the availability of data, the availability of compute powers, and also ready commercial applications. So these large-scale internet applications in speech recognition, in image classification, they were ready at this point. And I guess there was just not too much money in check reading for the economy to take notice back then. So this brings me to what we're doing today. Very similar technology applied to self-driving cars in this case. So first, an overview of the entire stack of NVIDIA self-driving. So we have at the bottom the hardware that goes into the car. That's the Drive PX family of products. The most recent is called Pegasus, that was just announced at CES. Then we have the operating system, real-time operating system layer. And then on top of that is DriveWorks. That's what I call the middleware. So that does sensor abstraction, does all the logging tools, inter-process communication, and it has low-level computer vision libraries such as image transformations. And then on top of that is Drive AV. This is the application layer. So this is where we put together all of the other technology to form actual applications. And some examples are here. This is sensor fusion from radar and camera. And this is LiDAR point cloud processing or deep learning-based object detector. So the detect the bus here or the pedestrians back there. This is deep learning-based free space detection. This is localization based on HD maps. And then this here is perception-based path planning. This is actually what comes out of our group in New Jersey. So what the New Jersey group is doing, we contribute into this layer here. And our goal is to solve the hard and unsolved problems. And I think there's a lot of those in self-driving car. So if I think back to character recognition, if we can't even program handwritten character recognition, then it's very likely that dealing with other humans and all kinds of different situations is likely not going to be solvable by just programming. So we concentrate on these hard problems for 2 reasons. One is that we want to provide algorithmic diversity. So in a safety-critical system, it's unlikely that you want to rely on any single algorithm. And the second reason is that we can solve functionality that might not be solvable otherwise, like taking turns just based on perception without map data, or learn to merge onto a busy highway where you have to negotiate with the other cars and squeeze yourself in. And then the other labs, the other autonomous labs in NVIDIA are in California, in Boulder, in Seattle, and in Europe. This is, we're actually back in the same building, which is cool. The building was empty for over 10 years, but it's now being redeveloped for mixed use. So there's a number of different tech companies in there. So NVIDIA is renting space around here. And there's also, we're going to get restaurants and shops. And on the rooftop, there's plans to build a hotel. The reason why we're there is not so much sentimental. It's because this is actually a very good environment for testing self-driving cars. We have plenty of space in the basement of the building to store and work on the cars. And then there's 2 tunnels here that we can take, and they lead us right up to these private roads here on the campus. Driving once around here is actually 2 miles. And then right outside, we have a very nice mix of highway, local roads, and residential roads. The location is also quite nice. So we're about 45 miles from New York City, and there's a train connection and ferry. So a train is about 60 to 70 minutes, and the ferry is faster, actually. You can take the shortcut, so it's around 40 minutes. So what is a typical case where rule-based systems struggle? Well, this seems clear, so we can detect these lane markings, localize the car within it, and then have a path planner and a controller and drive. But just about 100 meters further up on this road, the situation looks like this. So it's much harder now. So you have the double yellow line marker fainted, and then the center one is almost gone. You can still solve it, of course. You can build a detector for this curb or the fence. You may be able to reconstruct this yellow lane marking. Then you can measure the distance here and decide that this is actually wider than 1 lane. This is probably 2 lanes, and I'm currently here. So I'm going to assume that there's a virtual lane here, and I'm going to drive there. And then you have solved the problem for this scenario. And then around the corner, it's different again. So you have to start all over, and then again and again. So it seems a big advantage if we can build a system that can derive the domain knowledge from data. So by just observing humans, not by somebody telling it what it actually should look for in this scene. So this is one of the things that we built. If this is the lane here, that's where the car currently is, then we predict where would the human drive. So what is the short-term trajectory that the human would take given that image? And so collecting the data is relatively simple. You just drive. You can then derive this trajectory from the ego motion of the car. So the training labels, you essentially collect them for free without additional manual labor while you're collecting the data. And so then the difference between what the human drove and what the network predicts, that's the error signal that we backpropagate. This is an example network architecture. This is from about 2 years ago. It still looks similar, but it's growing, so we constantly adapt it to the current size of the training set. Oh yeah, good. The universal sign for auto. So these are all roads on our campus. And with this approach, it really doesn't matter whether the road looks horrible, grass overgrown, or is a nice highway. As long as we have data, we can learn from it. These roads are currently not used anymore on our campus, so that's just ideal for experimenting. So cool. So the voices in the background, they're not acting. This is actually real. We struggled so much to get this to work for an important demo deadline, and it was just about 12 hours before the drop dead deadline that this thing started working. So it was a big relief. So this is a made-up construction site with some unpaved section in the back. People often ask, well, if you train this in California, can you drive in New Jersey? So we showed it here. We trained with California data only and are driving here on a New Jersey highway. And here at night, it was drizzling slightly on an unpaved road in a nearby park.
Got it.
So we'll move on to something a little more practical. This is highway driving. So here we're driving. You'll see, here you see, this is what the network predicts what the human would drive. And you see that the lane markings here are lousy, and in part they're completely missing. And that doesn't seem to impress the network. It still predicts the correct trajectory. What you see here is we show the trajectories predicted from the most recent 10 frames, and then correct them for eager motion of the car, and then we show them all on top of each other. This is a debugging tool. If the network is confident, it will be consistent with its predictions over a few frames, and the noodles are nice and tight. And if it's not confident, then they'll spread out all over the place. It will predict something different each frame. So here, not to take that exit, or here again. This is all stuff that we haven't programmed. It just picked that up by observing humans. We're not limited to learn lane keeping. We can also learn lane changes. So this is a video showing that. The lane changes are triggered manually by, this is Cheney Chen here driving, and he's just tipping the lever for the turn signal. And that indicates to the car that it should now change lanes. We can also learn different lengths of the lane changes, so we can tell the car to complete the lane change in 200 meters, or 100 meters, or 50 meters. That's actually quite exciting at highway speed, completing a lane change in 50 meters. We can also learn to take turns. This was particularly exciting because I'm not sure there's really any other ways you could do this. So one of our internal goals is to be able to send the car on its own to get ice cream. And this is the route from the ice cream store back to the office with some detours to get extra turns. And you see the path that the network predicts here. Here's the entrance to our campus. So one of the things I mentioned before that it's important that, or an important aspect of our work is to learn by observing humans, not by manually programming things into the system. But nevertheless, we want to understand what it actually learned. So here we analyzed what it's looking at. The green regions, these are the regions that the network is sensitive to. And you see that it learns to detect these lane markings, which is interesting because we never labeled a single lane marking during training. Or here in a residential street, it learns to look at the cars. But if you look closely, it ignores the trees here. Or on our campus, if there's no clear lane markings, it learns to figure out to detect the road edges through other means. So this is a very important debugging tool for us. Here's a short video. You see lane merge. So while we're driving on the highway, it's looking at both lane markings, but this one will disappear in a moment. And now, instead of looking at both of a doubly wide lane, it's actually just following this one until the right one comes close enough so it becomes a single lane again. And it picked that up by observing. This is not us manually programming that into the system. At one point, someday we needed a screenshot from the inside of the car, and there's a lot of construction going on the campus currently, and this bobcat comes out into our roadway. And if you look here, the network prominently recognizes it, even though we're quite certain it's never seen this type of vehicle in the training before. So I wanted to close with some open challenges. In my mind, these are, well, we have tons of open challenges, but these are two of the big ones. One is to deal with ambiguous situations. So if you imagine you want to learn to merge onto a highway and you have a car right next to you, then you can either speed up and go in front, or you can slow down and go behind. But you can't do the average. So how we deal with that, how we can learn from where there's more than one possible correct way of driving, but you only ever get one of these possible options in each example. And then the other one is learn from imperfect behavior. So we have a ton and ton of data, but currently we need to cut out all the imperfect driving. You don't want to teach the network to cutting corners and such. And it does learn what you do, so it mimics the humans. So if we can get around and figure out how it can learn on its own what it actually should look at and what are outliers, then we would have a ton more data that we can work with. And so I'll finish with this video here. This was recorded recently in December. We got new data from a new sensor set of a new car fleet, and so the first 10 hours came in, all California data in the sun, very little night, no rain. And so the first thing we usually do is we train a network, we go out and test to see if it meets our expectation. This is kind of an end-to-end test to make sure that nothing's wrong with this new data. That day it happened to snow, so we were curious to see what happens. And it actually performed surprisingly well. So all this network has ever seen is California data, and it's now driving in the snow in New Jersey, or here at night on a partly snow-covered road with lights from oncoming traffic. You can also see what it's looking at, and it looks at what seems correct features on the road. Here it even looks at the tire tread markings in the snow, even though it certainly hasn't seen that in the original training data. And that brings me to the end. Thank you for your attention.